I was thinking about this the other day. When you play like a city building video game, upgrading your infrastructure is just, it's so incredibly clean.
Oh, yeah, totally frictionless.
Right. You just click a button, you spend some virtual coins, and boom, every single gas station on the map instantly turns into this sleek electric charging hub.
And all the little digital cars just automatically reroute themselves.
Exactly. There are no traffic jams,
Oh.
no construction delays, and definitely no multi-year permitting battles with your local zoning board.
I mean, it's the ultimate illusion of instantaneous progress. But when you step out of the simulation and into the actual real-world mechanics of the energy transition, you realize someone has to physically dig up the streets.
Yeah.
They have to negotiate the real estate and figure out how to keep the local power grid from literally melting down when a dozen high-powered vehicles plug in at the exact same time.
Which is exactly why we're here today. Because in reality, building something new means digging up those streets and completely overloading our old systems. Welcome to the deep dive, everyone. Today we are looking at the delightfully messy reality of 2026.
It is definitely messy out there right now.
It really is. The electric vehicle transition isn't failing, but it is fundamentally changing shape. We are finally moving out of that flashy early adopter hype phase and grinding our way into the hardcore, highly complicated hardware phase.
Which is where things actually get interesting.
Right. And to map this out for you, we've pulled together this incredible stack of sources. We've got Q1 market sales data, deep technical battery specs, and some fascinating urban freight studies.
It's a huge ecosystem to cover.
It is. So to really understand where this massive infrastructure shift is heading, we have to start by looking at what people are actually choosing to park in their driveways right now. Because the consumer adoption curve has hit a very real reset.
It really has. I mean, if we look at the first quarter reports for 2026, new EV sales in the U.S. actually dropped 27% year over year.
Wow.
Yeah, and the market share has sort of stabilized at roughly 5.8%. So on the surface, that looks like a massive step backward for the whole industry.
But context is everything here, right?
Exactly.
Because late 2025 saw this massive, totally artificial rush driven by the expiration of those federal tax incentives.
Right. Everyone was scrambling to get the deal.
Right. So automakers are now actively pulling back. They're resetting their production plans because that initial wave of, highly motivated, high-income early adopters has basically been tapped out.
Yeah, the people who were willing to pay that early adopter premium or who had the luxury of a dedicated home charging setup, they already bought their cars.
They're out of the market.
Right. We are now trying to sell to the broader mass market, and the mass market is incredibly price sensitive.
Which completely explains the absolute explosion we're seeing in the used EV market.
Yeah.
The data we have on this is just staggering.
It's wild.
While new sales dropped, national used EV sales grew 12%. They hit almost 93,500 units in a single quarter.
That's a huge jump.
It is. The average price is sitting around $34,800. But the most crucial number, and this is the one that really stood out to me, is that nearly 44% of those used EVs sold for under $25,000.
Right, and that $25,000 mark is so important. It's the psychological and financial threshold for true mass market affordability.
Yeah.
And what's really driving this is that the price gap between a used EV and a comparable used gas vehicle has practically vanished.
Oh, wow. Like, how much of a drop are we talking?
Well, back in 2023, you were looking at a $10,000 premium just to go electric on the used market.
Which is a huge barrier for most people.
Exactly. But today, that gap has plummeted to just $1,300.
That's nothing.
Right, and because of that, these used electric vehicles aren't just languishing on dealer lots anymore. They are selling in an average of 42 days, which is entirely on par with traditional gas cars.
Okay, let's unpack this a bit, though. I want to push back on the psychology of the current buyer.
Okay, go for it.
Because there is a specific detail in the market reports about the macroeconomics right now. It mentions that gas prices spiked recently due to geopolitical conflicts in the Middle East, right?
Right, everyone felt that at the pump.
Yeah. And the analysts noted that online searches for EVs surged in response. But wait, why didn't that surge spike immediately translate into actual new EV sales? If you're angry at the gas pump, shouldn't that be the exact moment you pull the trigger and buy one?
You would think so, yeah. But car buying simply doesn't operate on impulse.
Well, maybe for a pair of shoes, but not a car.
Exactly, not for the vast majority of households. The analysts point out a crucial distinction here. Searching is free.
Oh, that makes sense.
Right. It costs absolutely nothing to pull out your phone and Google the price of an electric SUV while you're standing the cold, pumping expensive gas.
Right, you're just window shopping to make yourself feel better.
Pretty much. But actually committing to a $40,000 or $50,000 multi-year financial obligation, that is a slow, methodical process. Shifting an entire industry's deeply ingrained buying habits just takes a massive amount of time.
Because you aren't just buying a car, you're buying into a completely new way of fueling and maintaining a piece of heavy machinery.
Precisely. Look at the historical timeline of hybrid vehicles.
Oh, good point.
It took hybrids roughly a 25-year journey of gradual consumer education to become these standard mainstream options that people buy without a second thought today.
Like, nobody even blinks at a hybrid now.
Right. And the EV transition is going through that exact same normalization process right now. It's transitioning from a market driven artificially by government policy to a mature market driven by basic economic fundamentals.
Okay, but if consumers are holding off on buying a brand new EV, affordability is really only half the equation, right?
Right. There's also the tech side.
Exactly, the technological anticipation. If you know a massive leap in battery technology is just around the corner, you might decide to keep your gas car for a few more years, rather than buy a lithium-ion EV that might feel like a dinosaur by the end of the decade.
1,000%.
And according to the technical specs we're looking at, that leap isn't just theoretical anymore. We are talking about solid-state batteries.
Yes. This really is the holy grail of energy storage.
It's what everyone's been waiting for.
It is. For decades, it was confined to university labs and these tiny, small-scale prototypes. Now it's finally moving into actual commercial production.
So for people who don't have an engineering degree, how does this
Ah.
actually differ from the battery in, like, my smartphone or my current car?
So to understand the magnitude of this shift, we need to look at the mechanics of traditional lithium-ion batteries. They rely on a liquid electrolyte.
Okay.
It's essentially a lithium salt dissolved in an organic, highly flammable solvent. And this liquid acts as the medium for the ions to move back and forth between the battery's anode and cathode.
Okay, so an analogy here. A traditional battery is kind of like a swimming pool. The ions are the swimmers, and they can easily glide through the liquid water from one end of the pool to the other.
Yes, that's exactly it.
But the problem is that water, or in this case, the highly flammable solvent, can slosh around, it can leak if the pool cracks, and if things get too hot, that liquid can literally boil over and catch fire.
That is a great way to visualize it. So solid-state technology completely drains the pool.
Oh, wow.
It replaces that liquid solvent with solid materials, typically things like polymers, oxides, or sulfides. Sticking with your analogy, it's like replacing the swimming pool with a high-speed rail network embedded in solid rock.
Which instantly solves the flammability problem.
Entirely.
Because the safety upgrade here is just
Yeah.
immense. The data notes that thermal runaway, which that's the specific point where a battery begins an uncontrollable chemical fire, right?
Right, the scary stuff.
That happens at just 90 degrees Celsius for a traditional liquid battery. But for these new solid-state batteries, that thermal runaway threshold jumps all the way to 247 degrees Celsius.
And because that massive safety risk is basically removed, engineers can finally use much more volatile but far more energy-dense materials.
Like what?
Specifically, they can use pure lithium metal for the anode.
Okay, why couldn't they use that before?
Because in a liquid battery, pure lithium metal creates these microscopic, needle-like structures called dendrites. They literally grow across the liquid and cause short circuits.
Oh, so they just pierce right through it.
Exactly. But a solid barrier physically blocks those dendrites from growing. And this simple material swap unlocks an energy density of 400 to 500 watt-hours per kilogram.
And in practical terms, for you listening, that density leap is what gives us the magic numbers. We're talking a range of over 1,000 kilometers on a single charge.
It's incredible.
And they can fast charge to 80% in just 10 to 15 minutes, while remaining totally operational in extreme weather down to negative 40 degrees Celsius.
Which is a game changer for cold climates.
Totally. And the sources also mentioned a really interesting secondary market for this. E-bikes might actually get this technology on the streets before mass market cars do.
Yeah, that makes a lot of sense.
Because the battery footprint is so small, an e-bike could potentially double its range up to 200 kilometers while cutting the battery weight in half. But this is where I have to pause.
Okay, what's the catch?
Right. If this technology fundamentally solves range anxiety, charging times, A&D fire risks, why isn't every single car rolling off the assembly line right now using a solid-state battery?
It all comes down to the staggering difficulty of manufacturing them at scale. Remember the high-speed rail embedded in solid rock?
Right.
Well, the problem with solid materials is that they do not naturally conform to each other.
What do you mean?
When you pour a liquid electrolyte into a battery casing, it effortlessly fills every microscopic nook and cranny, creating perfect contact for the ions to flow.
Sure, because it's a liquid.
But when you press two solid blocks together, no matter how smooth they look to the naked eye, on a microscopic level, they are full of jagged peaks and valleys.
Ah,
This creates what engineers call interface resistance. If the solid layers aren't mating perfectly, the ions get stuck in the border. Basically, the train derails.
so the friction of just getting the ions to cross from one solid material to the next ruins the battery's efficiency.
Exactly. And fixing that requires incredibly complex manufacturing environments. For example, some companies are using sulfide-based solid electrolytes because they have great conductivity.
That's good so far.
It is, but the moment a sulfide material is exposed to even trace amounts of humidity in the air, it reacts and releases highly toxic hydrogen sulfide gas.
That's bad.
Very bad. So you have to build these ultra-dry, hermetically sealed factory environments.
Wow.
On the other hand, you have companies using oxide-based materials. Now, those don't create toxic gas, but binding them together requires a process called sintering.
Sintering, meaning they have to bake the batteries.
Yes, at temperatures reaching 1,000 degrees Celsius.
You're kidding.
Nope. Trying to scale up an assembly line that requires baking millions of battery cells at 1,000 degrees uses a catastrophic amount of energy, which drives the unit cost completely through the roof.
So that's a bottleneck.
It is. This is why we're currently only in phase 2 of the solid-state rollout. We're seeing initial low-volume production strictly for ultra-premium vehicles where the profit margins can absorb those crazy manufacturing costs.
Right, the luxury cars get it first.
Exactly. True mass production, the kind that ends up in a standard family sedan, won't be economically viable until the 2030s.
Which is fascinating.
Yeah.
But look, even a battery that holds twice as much energy is completely useless to a commercial fleet if it takes hours to fill.
So true.
If we look at this from a systemic level, the vehicle itself is only one half of the equation. The way we actually deliver power to these vehicles is arguably the much larger bottleneck, especially for commercial operators.
Right. Downtime is the enemy.
Exactly. If an Amazon van or a robotaxi is sitting parked and plugged into a wall, it is actively losing money.
That downtime is exactly what's forcing the industry to completely rethink the actual mechanics of the plug-in process.
Yeah.
And the Q1 charging market data shows this shift happening in real time. The public fast charging network in the US is finally stabilizing.
Which is a relief.
Oh, absolutely. We're seeing reliability rates consistently hitting between 90 and 95% now.
Which is a massive upgrade compared to the broken screen error code nightmare we all dealt with a few years ago.
Seriously. And high power charging, meaning 250 kilowatts or more, is now the industry baseline. It accounts for 67% of all new installations.
That's huge.
And the utilization of these chargers, like how often a car is actually plugged in and drawing power, is holding steady at 15.6%. Prices are also stable, around 53 cents per kilowatt hour.
We're also seeing some shifts in who owns the ports, right? Tesla's dominance in new charging ports has slipped from 40% down to 26%, though they are still building these massive 12-port hubs, while competitors mostly stick to, like, 4-port stations.
Right. But the most radical shifts aren't happening at public highway stops. They're happening in the commercial fleet yards.
How so?
Imagine you're a logistics company trying to electrify 50 delivery vans. Upgrading your depot to handle 50 high-speed chargers requires trenching concrete, pulling heavy copper wire, and waiting up to 2 years for the local utility to install a new multi-megawatt transformer.
Yeah, the permitting alone could bankrupt a small logistics firm.
Exactly.
Which completely explains the rise of charging as a service. The reports we looked at highlight companies like SparkCharge that are basically bypassing the local electrical grid entirely.
It's such a clever workaround.
It is. Instead of making the fleet manager build a charging hub, they literally drive a massive off-grid battery trailer directly into the seat yard. They charge the vans from the trailer overnight and then tow the empty trailer away to be recharged somewhere else.
It entirely removes the grid delay and that massive upfront capital expenditure.
Right.
It is a profound shift in infrastructure logic. You're decoupling the charging station from the physical real estate.
Right. The power comes to you.
Exactly. And that decoupling is essential when we look at the autonomous fleet market. Uber, for example, just announced a $100 million investment with EVgo to build dedicated fast-charging infrastructure in major cities, specifically to support robotaxis from companies like Waymo and WeRide.
Right. And to make those massive real estate deals work, Uber is using something called minimum utilization guarantees.
Yes.
How exactly does a financial mechanism like that accelerate the physical infrastructure? Like, how does a contract build a charger faster?
By completely shielding the hardware providers from risk. Think about it. Building a multi-million-dollar charging hub for robotaxis is a huge gamble for a company like EVgo.
Because what if the robotaxis don't show up?
Exactly. So a minimum utilization guarantee means Uber contractually promises that a certain percentage of that charging capacity will be paid for no matter what.
Oh, wow.
Yeah. If utilization drops below that threshold, Uber literally writes a check for the difference. It provides the financial certainty needed to pour concrete and secure loans.
And it isn't just the financial mechanics that are changing, it's the physical interaction, too.
Mm.
Companies like Joule Labs are rolling out their AURA systems.
Mm-hmm.
These are robotic charging arms.
Right, the automation piece?
Yeah, because if a robotaxi doesn't have a human driver, it needs to be able to pull into a depot, have a robotic arm, identify the charge port, plug itself in, and disconnect completely autonomously.
But, this actually brings up a tension between the different technologies we're discussing today.
Right. I see where you're going with this.
Yeah.
If solid-state batteries are about to hit the market and promise to double a vehicle's range, are companies like Uber making a huge mistake by pouring hundreds of millions of dollars into dense urban charging hubs right now?
It's the obvious question, right?
Right. If a robotaxi can suddenly drive 1,000 kilometers on a single charge, won't these massive fast-charging depots become totally obsolete?
It is a totally valid concern, but it misinterprets the relentless math of autonomous fleet economics.
Okay, lay the math on me.
A robotaxi or a robotic delivery van does not behave like your personal vehicle. Your personal car sits parked and idle for roughly 95% of its life.
Sure.
But an autonomous vehicle operates continuously, day and night. It's a highly utilized capital asset. Even if you double the battery range, a vehicle running 24 hours a day in dense city traffic is going to chew through that expanded capacity incredibly fast.
So they still require high-density automated turnaround charging just to be in the field and remain profitable.
Exactly. That steady 15.6% utilization rate across the industry proves that operators aren't overbuilding.
They know exactly what they're doing.
Right. They are getting incredibly sophisticated at using data logistics to match their power supply directly to their fleet demand. The infrastructure is essentially sizing itself to the actual need.
Okay, so we have this incredible, highly optimized web of continuous operations. Autonomous vehicles powered by increasingly dense batteries, fueled by robotic chargers and off-grid mobile power stations.
It really is a logistical marvel.
It is. But eventually, those autonomous vehicles and delivery vans have to drop off their packages. They have to enter the physical, messy space where we all actually live.
And that's where the friction happens.
Exactly. Which brings us to the ultimate bottleneck of this entire ecosystem, the city curb.
Yeah, the last mile of delivery is the most expensive, the most complicated, and frankly, the dirtiest segment of the supply chain.
Absolutely.
According to the urban freight data, half of all road-based freight emissions occur in that final mile between the local warehouse and your front door.
Half. That's insane.
Right. But addressing this in the United States requires navigating incredibly complex legal barriers.
Right, because unlike Paris or London, U.S. cities operate under strict federal preemption laws, specifically the Clean Air Act.
Exactly.
A mayor in a U.S. city cannot simply pass a law banning gas-powered diesel trucks from entering a downtown commercial district. They literally do not have the legal authority to regulate interstate commerce or set local vehicle emission standards.
Which is a huge constraint for city planners.
So because they can't use a blunt ban, they have to use highly creative, indirect levers to force logistics companies to clean up their fleets. And the two most effective levers right now are mode shift and space management.
Mode shift is exactly what it sounds like, moving freight out of heavy, dangerous trucks and into smaller, cleaner microfreight vehicles.
Like bikes and stuff.
Yeah. For instance, cities are heavily subsidizing cargo e-bikes. Boston is actively using grants to subsidize cargo bike fleets, and San Francisco is providing financial incentives for gig economy food delivery workers to trade their gas cars for e-bikes.
That's great. But the truly fascinating lever to me is space management,
Hmm.
because the city curb is essentially the most fiercely contested real estate on the planet right now.
Oh, absolutely.
It's a high-stakes, real-time game of Tetris involving pedestrians, massive Amazon step vans, cargo trikes, and those little cooler-sized sidewalk delivery robots.
All fighting for the exact same 5 feet of concrete.
Right. And cities are realizing that while they can't ban a diesel truck, they completely control the parking spaces. So how exactly are they digitizing that control?
By using tools like the curb data specification, Portland is actually a great example of this.
What exactly is that?
The curb data specification is essentially a digital API for the physical street. It allows the city to create dynamic digital geofences.
Okay.
So Portland used this to establish zero-emission loading zones. Instead of just putting up a metal sign that a driver might ignore, the zone is digitally mapped. If a clean electric cargo bike pulls into that space, it pays nothing. But if a diesel truck parks there, the digital system can immediately flag it for a penalty or dynamically adjust the price of that curb space to be prohibitively expensive for a high-emission vehicle.
Oh, that's smart. It fundamentally changes the economics of parking.
Exactly.
But they're also managing space by changing where the packages actually go, right? Like New York City is permitting public carrier-agnostic parcel lockers on sidewalks through companies like GoLocker.
Which is huge for managing packet flow.
It is, but I have to play devil's advocate on this entire urban freight strategy for a second.
Let's hear it.
If we take one massive diesel delivery van, right, and we replace its cargo capacity with a swarm of 10 electric cargo trikes and 20 autonomous sidewalk robots, aren't we just relocating the congestion?
How do you mean?
Like, we take it off the asphalt street and dump it directly onto the pedestrian sidewalk. That sounds like a nightmare for anyone just trying to walk their dog.
That is the exact fear many urban planners had, but the data tells a completely different story. Yeah. It comes back to the power of behavioral consolidation. Let's look at the parcel locker data. When a city installs these shared public lockers on the sidewalk, it reduces the delivery truck dwell time at the curb by up to 33%.
Okay, that's a big drop.
But, more impressively, it slashes the overall delivery time by 78%.
Wow. Wait, just because of the lockers?
Yeah, because the driver isn't making 50 separate stops at 50 different apartment buildings, circling the block, looking for parking each time, waiting for elevators.
Right. They just drop it all in one place.
Exactly. They make one single stop at one consolidated locker bank. The introduction of the locker doesn't just swap a gas vehicle for an electric one. It fundamentally alters the behavioral flow of the goods.
It streamlines the entire process.
Right. By consolidating the drop-off points, the entire logistics network requires significantly fewer total trips. It's an efficiency multiplier that actually reduces overall traffic, regardless of what kind of vehicle is doing the delivery.
That is absolutely brilliant. It isn't just about building cleaner machines, it's about altering the geometry of how our physical world operates to require fewer machines in the first place.
Exactly.
And that really connects all the threads we've pulled today. We started by looking at price-conscious consumers snatching up $25,000 used EVs because the economics finally make sense.
Right.
Then we explored the deep chemistry of solid-state batteries trying to survive 1,000-degree ovens just to unlock 1,000 kilometers of range.
And the robotic arms that are going to charge them.
Exactly. We broke down the financial mechanics of minimum utilization guarantees funding those robotic arms, all the way down to the digital APIs and public lockers, completely rewriting the real estate of your local sidewalk.
It is a deeply interconnected ecosystem. A breakthrough in battery density directly impacts how long a robotaxi can operate, which directly alters the financial models for those urban charging hubs, which ultimately changes what kinds of vehicles are fighting for space outside your front door.
And it serves as a great reminder that the next time you, the listener, browse for a used car online, or order an autonomous ride, or just casually click Buy Now on a package, you are actively participating in this massive, messy, real-time rewiring of our infrastructure.
It does leave us with one final, rather provocative thought to consider, though.
Okay, lay it on us.
We are rapidly deploying robotic charging arms, autonomous delivery drones, and algorithm-driven sidewalk droids, right?
Yeah.
We are actively building a physical layer of city infrastructure that is designed entirely for machines to interact with other machines. The delivery robot communicates directly with the parcel locker. The robotaxi communicates directly with the charging arm.
Oh, wow. Yeah.
So as this machine-to-machine infrastructure scales, at what point do we, as humans, start to feel like guests on our own city streets?
Man, that brings us full circle right back to that SimCity comparison.
Hmm.
In the simulation, the people are just tiny pixelated decorations wandering around the perfect infrastructure you built for them.
Pretty much.
But real life doesn't have a clean, instant upgrade button. The transition is incredibly complex, it demands deep technical problem solving, and we actually have to share the physical space with these upgrades as they happen.
Ready or not.
Exactly. Ready or not, the hardware phase is here, and we are all playing the game right now. Thanks for joining us on this deep dive, everyone.